All right, here we go. Let's take a look at chapter 3 here. You're going to love this chapter. Basically, I'm going to teach you how to do derivatives and all that long stuff that Mr. Bean showed you. Yeah, I'm going to teach you the shortcut to all of that. So this is going to be a great chapter. Let's start things off with notation. Two major types of notation. We got Lagrange here and we got Leibniz. These are the two main ones that pretty much everyone uses for calculus. So if I give you some kind of function, some kind of f, this is its derivative here. This is called f prime. It's the derivative of a function. A lot of times we say the f of x. So this would be the f prime of x. So that's Lagrange. He's an Italian dude who made this one famous. Over here, if I give you y to find the derivative, I'm going to use y prime. And this one can look a little different. Same thing with y. This is the derivative of y with respect to x. Sometimes we write it using parentheses, the derivative of y with respect to x. So sometimes you may see it like that. So Leibniz is a cool dude, German mathematician. Not only did he do calculus, just as important, I don't know if you've ever had these butter cakes before, but they are delicious. Two other people who did stuff, I mean lots of people did stuff, but Euler has a notation you may run into. It's a big fat capital D and then like this, but you don't really see it very much, so probably never going to run into Euler's. And Newton, you may know Newton. He does some stuff there too. He's also credited for calculus. His notation never made it. He was trying to put dots on top, didn't make it. So really, if you're good with Lagrange and Leibniz, that's good. If you have a hard time saying those because maybe you can say the American version, you can say Lagrange if you want, or Leibniz, I don't know. As long as you recognize them, you're good to go. So let's do this. Let's take some derivatives. Before we start taking derivatives, why are they so important? Here's a quick little video. I'm always going to show this, derivatives. All right, so here I have a function here in blue, and if we take a point on this function, we're going to look at the derivative. So what does the derivative mean? Well, the derivative at this point is the slope at this point. So what's great about that is that's going to give us the slope of the tangent line. And this is so important because the slope of the tangent line is the instantaneous rate of change. So if you look at I went ahead and graphed the tangent line there. If you look at that, the slope of that is positive. So if I go ahead and kind of animate this point, it is a positive increasing function until here. Boom, all of a sudden, now I'm looking at a horizontal tangent line, which, as you can tell what's happening here, I hit a maximum point. Then if we keep this going, you can see that is a negative tangent line. So what does that mean if you have a negative derivative? Well, it means you are a decreasing function. So in this little area, I'm decreasing again until I hit this point up here. Boom, there it is, another horizontal tangent, and in this case it's actually a minimum point. So the derivative is the slope at a point, it's the slope of the tangent line, and is the instantaneous rate of change at that point. Now we're going to use this for all kinds of things, as you can see, to find maximum and minimum points and determine if my function is increasing or decreasing. Okay, so I'm going to keep hammering that because the derivative is so important. So we're going to just practice taking these and come across some of those little applications along the way. So if I want to find the derivative, I'm going to find f prime of x. I'm going to do it, then I'm going to give you the power rule, which is the most basic rule of all this stuff. Do it with me, and we'll see if you catch the rule as we go. Basically, here as I go, the first one is going to be 21x to the 6th. This first term here, how am I doing that? I'm going to go 7 times 3 is 21. Then I'm going to drop the exponent 1, so it's 6. So what's going to happen here? 5 times 4 is 20. Drop the exponent down 1 is 4. And what am I going to do here? 3 times a third is 1. Drop the exponent down to 2. If there's no coefficient, 2 times 1 is 2. Drop the exponent down to 1. This has an exponent of 1, so what am I going to do? 1 times 3. This is x to the 0, but what is anything to the 0 power? Anything to the 0 power is just 1, so I'm not even going to write it. Those are nice. And then, technically speaking, this is x to the 0. Well, 0 times 7 is gone, so constants will just disappear. Boom, they're gone. So this is the derivative. Could you imagine doing that longhand notation with this? Holy cow, that would take you probably the rest of today. Remember doing this bad boy, the limit as h approaches 0? If you plug this whole thing in there, could you imagine taking x to the 7th power, x minus h to the 7th power? It would be awful. We're not going to do this anymore. We're going to do the shortcut. It's the power rule. It is awesome. Let's try it again. So does it work for negative numbers? Sure. If I want to find y prime, what do I do here? I'm going to take the exponent, multiply by the coefficient, so this is negative 7x. Drop this power 1, so you're subtracting 1, so this actually becomes negative 4. Again, this has an exponent of 1, so this becomes plain old 4. Don't be confused by pi. Pi is a number, 3.14. It's a constant. It doesn't have anything, so it goes away. So the constants will just drop, just like the 7 disappeared. These are the derivatives. Isn't that awesome? So what is the power rule? If I have any variable to raise to the nth power, I'm going to take n and times it in front by the coefficient. So it'll be n to the x. And then what's going to happen to my exponent? I'm going to drop it 1. Boom. That is the power rule. Constants just go to 0. They are gone, and I'm going to write that up at the end. Sweet. Let's do some of these. Let's bring the pain. All right. Wait a minute, the rule doesn't work. First one, great example, Mr. Bruss. But yeah, check it out. We have to rewrite things. So that's the key to derivatives. We're going to rewrite, differentiate, and then we're going to simplify. So if I'm trying to find the derivative, before I do it, let's rewrite this. Remember, this is really what? As a rational exponent, or as a fraction exponent, it's 7 over 3. Minus, what is this? This is x to the 1/2. Square roots are like the square. Remember, there's like a little 2 here. And then the next one is going to be 2 times, what is this? Square goes on top, 5 goes on bottom. So the root is the bottom of the fraction, the root, and then the power goes on top. So boom, we did the rewrite. Now let's differentiate. Let's take that derivative. And what happens here, 7/3 comes in front. 7/3 times 1 is 7/3. Drop this power, so we got to be good with fractions. 7/3 minus 3/3 is 4/3, or minus that 1. What happens here? You got the 1/2. And then 1/2 minus 1 is negative 1/2. And we've got 2 times 2/5, so this is going to give me 4/5. And then what do? Drop that power, so you're subtracting 5/5, so you end up with minus 3/5. He says a 3. There it is. So that's good, but then we're going to go ahead and practice simplifying it. AP exam, if it's a free response, you're done. Leave it there. But a lot of times, that's not going to match your multiple choice thing. So we got to go ahead and do the simplify part of it. So my answers, I want you to go ahead and simplify them. First one is good to go. If you want to take it back, let's take it back into what? It's a cube root of x to the 4th. Boom. Take it back to its radical form there. Then what happens with this? We've got this minus 1/2, but it's a negative exponent, so he moves to the bottom. So that square root is actually on the bottom. That's a square root. Negative sign puts at the bottom, and 1 over 2 there. Excellent. Also another negative square root here, so the 4 stays on top. The x is going to join the 5 on the bottom. What are we looking at here? This is the 5th root of x cubed. Excellent. So if you're okay with rewriting things, it's the same rules. You'll be good to go. So rewrite, differentiate, and simplify. All right, I'm going to go ahead and do the next one with you. If you want to work ahead of me, that's fine. Oh, I got ahead of myself. I can't work ahead of myself. Let's go ahead and what do we do first? We got to rewrite this one. So I'm going to rewrite this with negative exponents. So I don't like this in the bottom of the fraction. I can't do my power rule to it, but check that out. That just means x to the negative 1. What is this? This is 4x to the negative 2. If you did our summer packet, this maybe is all coming back to you. This is why I was in there. Okay, so before I rewrite this one, I'm actually going to go ahead and square that bottom. That whole bottom square would be what? 9 over x squared. So it's squaring both the 3 and the x. So now when I rewrite it, I like the fractions are cool. I like the 1/9, but I don't like the the variables in the denominator. So our whole goal is to get those things out of the denominator so we can use our rule. So this is really, because the 2 is on both of them, it's really 1/9. So that's kind of a tricky one there. So we rewrote it. Now let's differentiate. Boom. So I'm going to follow my rules. Power times the coefficient. Drop it 1. Then I'm going to say negative 2 times 4. Let's just go ahead. I like to make that negative 8 as I go. So we'll say that'll be negative 8x to the negative 3. You could say plus minus, but it gets confusing in there. So I've got a negative 1/9 times a negative 2. So I'm looking at plus 2/9. And that is x to the negative 3. So I'm pretty happy with that. There's my derivative. Now let's simplify it. And what is this going to do? I'm really just going to move my exponents back to the bottom. They're going back to the denominator. So the negative brings it down. Minus 8 over what? X cubed, because it's negative 3. And then plus the 2/9. But joining the 9 back down here will be x cubed. Excellent. There you go. So that's a simplified form. Very nice. So we're getting it. Excellent. Here's another rewrite one. So this is a great one here. Sometimes I need to break up the fraction. So it'd be weird if I try to bring this 2x up. You can do it, but that's going to be later on. I can split this fraction up. So let's rewrite this as 3 separate fractions, because there's one term on the bottom. Take every term on top and divide it by that one term on top. So negative 16x squared over 2x plus 5x over 2x minus 1 over 2x. So this is like a double rewrite. So I rewrote it so I could rewrite it. Crazy time. What happens here? Hopefully some good things are going to happen here. Well, the x cancels one of these x's. The 2 cancels that 8 times. So I'm left with negative 8 x. How about this guy right here? Boom, boom. My x's cancel, so I have 5 halves. And then I can't cancel anything here, but I can rewrite this, can I? This will be 1 over 2. If I want that x to come to the top, I got to make it a negative 1. So there we had a double rewrite. So now we can take the derivative. So now I'm ready for f prime. What happens here? This is a great one. This just turns into negative 8 because remember that's an exponent of 1. Drops down to 0. We don't write it. Constant. Constants disappear when you go take the derivative of them. And then a negative times a negative is positive 1/2. X to the negative 2. So we got the derivative. Let's just have some closure here. Wrap this bad boy up. I want to put that x back on bottom. So a lot of variety right there. If that all made sense, I went really fast. You got to watch that again. Pause it. Think about it. That's it, though, man. We're going to rewrite, take the derivative, simplify. Oh, and we're going to evaluate. So let's do the same thing. Just throwing in there if we want to evaluate it. So this one I don't need to rewrite. I can go straight to the derivative. So 4 times 1/2 is 2. Drop that power 1 is 3. Negative 2 times a negative 4 will be plus 8x to the negative 3. What happens to e? Gandhi. He's nothing. He's a constant. So when I take the derivative, he disappears. So I'm trying to evaluate. Before I evaluate this, though, I'm going to rewrite it because I don't like that negative exponent. So I'm going to move that x cubed to the bottom. Now I am ready to do a little plug and chug. I want to find the f prime of 3. So this means what is the derivative when x is 3? Plug this bad boy in here. And now it's just a matter of cleaning this thing up here. So 3 cubed is 27. Times it by 2 should be 54. And over 8 over 3 cubed is 27. And, oh, this is nasty looking. I don't really want to go beyond that. This is not a very friendly one. I'd leave that alone because if I get a common denominator, that number is going to be huge on top. So I'll be pretty cool with this. This would probably be one that would be a calculator one, so you can make it a decimal for this one. Great example, Mr. Brust. All right, how about this? So this is actually the same as f prime 3. This is saying what is the derivative of 4. If it was in Lagrange, it would be f prime of 4. That's the same thing. So if it looks like it means take the derivative, take the derivative. So boom, I'm going to rewrite this one first as what? That is x to the negative 1/2. Then I'm going to differentiate. Boom. And I've got what? Negative 1/2 times 1 is negative 1/2 x. Drop that power again, becomes negative 3/2. Derivative of 4x, just plain old 4. I love those. Now I'm going to do a real quick rewrite. And what's going to go? That's going to go back to the bottom. So I'm looking at the square root of x cubed on bottom plus 4. I hope this works out friendlier than the other one. Go ahead and plug 4 in there now. You get negative 1 over, what is 4 cubed? Woo, we got some big numbers here. 4 cubed is what, 64? And then if I square root it, I get 8. So I really get 1 over 2 times 8 plus 4, which is negative 1/16 plus 4. This is one I could actually simplify without beating myself up too much. It should be what? It should be 3 and 15/16. If you want to make that an improper fraction, you can say 48 plus 15, I think is 63/16. Woo! That is great right there. Good stuff. Evaluating derivatives. Why are derivatives so important? Derivative is the slope at a point. It's the slope of the tangent line and is the instantaneous rate of change at that point. All right, very good. Let's do some higher order derivatives. All this means is we're going to do the derivative multiple times. So this is f prime, this is f double prime, f triple prime, and this would be the 4th derivative. So at some point we have to say f to the n. So that would be whatever n is, the 17th derivative. Probably not going to go that far, but I guess you could. So let's do the first one together. So it's kind of like the one we started with. If I want to take the first derivative, I'm going to go through these quick now. Boom. 4 times 2 is 8. Go ahead and say 10x minus 3. So there's the first derivative. Now I want the second derivative. So we definitely use the second derivative quite a bit. So I'm going to do it again. 3 times 8 is 24. And then I want the third derivative. So it actually has some real life meaning to this. So 42, dang it, why did I pick big numbers? I think this is 210. And, oh, wait, I messed up there. 2 times 24 should be what? 48x. Constant disappears. And that's what happens when you start taking multiple derivatives here. They get smaller and smaller. And the last one, this should be what? 840 x cubed minus 48. So that's the fourth derivative. You go for a while. Eventually, you're going to run out of and hit 0 because these powers will dwindle away. But these are higher order derivatives. It means taking the derivative a couple times. So over here in Leibniz notation, this is the first derivative. This is the second derivative. So this. All right, so I rewrote the equation here. Then I found the derivative here, and I kind of wrote to the side. There's the simplified version right there. But it's easier since I have this right here to take the derivative of this again to come straight down to this. And I didn't show the work on that. I went straight to simplification. Hopefully you got those answers. If not, double check them. Excellent. This is great. Now, what about something like this? If I want to find the derivative, and if actually I want to evaluate at a point, I can't do this one. Square roots, I haven't talked about that yet. Eventually you will, so we're going to do them in the calculator. So the calculator is a fantastic tool here. So you can put in 1/2. Let's put it into your y equals. You want to find a derivative? Mr. Bean showed you one way to do it. I'm going to show you another way to do it. So type this into your y equals. So I've got 1/2 x. You could use 0.5 if you like. Minus 1. So there's my square root. Then I'm going to graph this bad boy, and you can see it. There it is. So the derivative at 4 is what we're looking for. So all you're going to do is hit calculate, and you're going to say, there it is, number 6, dy dx. Boom. Going to hit enter, and I got nothing. That is a bummer. Let's try that again. So maybe because it's undefined at 0, let's come over here to 4 first. So at 4, it makes this point. Let's try this again. The derivative, number 6, at trace 4. There it is right there. So sometimes if you're not on your graph, it may be kind of weird. I'm going to save that over here so you can see it. So at 4, the derivative, that did not show up very well, is what? It is 2.07. You can either say 8 or 9 depending on how you round that one. You're good to go. So this is great if you are just trying to find the slope of the tangent line at the point, maybe 4. Can you do it with e as well? Sure thing, not a problem. Come back to this. Find the derivative with what? When it goes to e, there is an e button here. So if you hit second divide sign, there it is. Gives you the derivative right here. I'm going to drag that bad boy over. I don't know why they're not showing up. So we get 1.698. Excellent. Go ahead and pause it. Try the trig function over there. Okay, so here we go. Couple things. Cosecant, remember, is 1 over sine. So again, this is some summer packet stuff there. So I hope that you put that in correctly. Make sure you zoom trig. You should get a picture like this. So I kind of messed with you a little bit here, didn't I? First one, what happens when you put pi in? Well, pi is right here, isn't it? So that is a bummer. It's actually on this vertical asymptote. So it doesn't exist. So this is impossible. There is no derivative here. It's undefined. How about a pi over 2? It's right here. It's kind of hard to see over here. It's a little fainted there. But what's the derivative here? It's 0. And that's such an interesting thing. That means the slope of the tangent is 0 right there. So cool if you drew in the tangent line. So it's a minimum point. That is awesome. All right, so moving on. Remember that little clip I showed you? The derivative is the slope at a point. It's the slope of the tangent line and is the instantaneous rate of change at that point. Well, here it is, man. Slope at a point, slope of a tangent line, instantaneous rate of change. So let's do it. If I ask you to find the slope at the point when x is 2, what are you doing? You are finding the derivative at that. So plug and chug right here. You should get 2x, drop the power 1. This is just 1 right here, and the constant disappears. So this is great. So if I want to know the slope at the point when x is 2, all you're doing is plugging 2 into this bad boy, and you should get what? 2 times 8 minus 1 is 15. So the slope at this point is 15, so that is the derivative. So in something like this, I actually prefer Lagrange method. It's so much nicer to look at this, the derivative. So when x is 2, the slope at that point is 15. How about this? Write the equation of the tangent line. It's the same problem here, so we know the slope. So if I want the tangent line, remember we did this before, I'm going to use point slope form. So when x is 2, I need to know the y value. Equals the slope, which is 15. I know the x value is 2, so here's point slope form. The key is what is the y value? Well, you got to plug it in here. So if I plug 2 into my equation, it's kind of congested here, this will give me the y value. And what is that y value? If I clean that all up, 2 to the 4th is what? 16? And then 16 and a half is 8. Minus 2 plus 2 is going to be 8. So this is the point 2 comma 8. So you got to find the whole point here. So I just gave you x is 2. You got to find y is 8. That way you can do Boom, point slope form. Point slope form. Awesome. How about this instantaneous? Oh, before we do it, let's graph it to make sure I'm right. So another little cool thing with the calculator is you can double check it. Okay, so just watch me. Don't do this one yourself. I went ahead and put the equation in there that with the original equation. I went ahead and put our derivative. I solved this. I put an mx plus b form, 15x minus 22, same thing here. And if I zoom, graph this, check it out. So I should get the original function. There it is. And then is that the slope of the tangent line at 2? It sure looks like it, doesn't it? So it's hitting right here. Boom, there's the tangent line. It looks perfect. So a great way to check if you're allowed to use a calculator right there. Excellent. If I ask you to find the instantaneous rate of change, what are you doing? You're doing the same thing. It's all derivatives here. I want to know what's the instantaneous rate of change at 3. So I'm going to find the s prime of 3. S is usually used for position function, t for time, and this looks like a gravity thing. So we're negative 4.9 meters per second. So let's multiply that out. Real quick, let's take the derivative. So that'll be 9.8. Drop it 1. Drop it like it's hot. And then the t goes to just 40. Can I put 3 in there and evaluate? Sure. So plug in 3 here. And what do we end up getting? So if you multiply that out, blah, 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 we're at the 40, you should get 10.6. Hopefully you're impressed by that mental math. I'm just kidding. I checked in the calculator beforehand. All right, so what does that mean? That's a great answer, but it's instantaneous rate of change. We're always going to label these things. So if it's something falling, this is a rate of change. It's probably going to be something like maybe you're falling 10.6 meters per second. Now, I'll definitely give you a word problem. I just knew that this was meters from gravity formula. It's something like this. So it's going 10.6 meters per second. That's the beauty of derivatives. That's what we're going to keep doing here. Wrapping it up, we got the normal line. What in the world is a normal line? The normal line is just perpendicular to the tangent line. So it's the same thing. If you can find a tangent line, you can definitely find a normal line. Let's do it. So first things first, I want to do it when x is 3. So I want to graph this one. So I'm thinking about this point here. So I can kind of see the tangent line is roughly like this. You can draw on a tangent line. So what's the normal line going to be? It's going to be perpendicular to that. So it's going to look something. Whoa, I hope your line's straighter than that. Got a little wonky there. It's the perpendicular line. So this is the normal line right here. So first things first, let's find when x is 3, what is y? I'm going to cheat and use a picture. You could find the f of 3, but if I plug 3 in, what comes out? Well, here it is right here, negative 3. So there's the point in question. So let's go ahead and find the derivative and multiply this out. We get 3x squared minus 8x plus 1. And now let's evaluate when x is 3. So the derivative at this point, when you plug in 3, my handwriting I feel like is deteriorating worse and worse here. 3 squared is 9, so we're looking at 27 minus 24 plus 1. So the f prime of 3 is what? That looks like 4. And would that make sense for this? That means what? It means I didn't draw my tangent line very good, but the slope here would be what? Up 4, 1, 2, 3, 4 over 1. So my little approximation was not so good, but if I use like a real person straight line, this would be the tangent line right there. So that seems to make more sense than my little hand-drawn picture there. So I'm going to delete it. There's the tangent line, but I want the normal line. So if I want the normal line, I want the negative reciprocal of this. So let's go ahead and write it. I'm thinking about my point. Oops, let's use a different color than that. Let's use purple. So I'm going to go straight to point slope form. I'm going to say my y value is negative 3, so this will be y minus a negative 3 or plus. Then I want the 1/4, flip it and change the sign. So that's the negative 1/4 is the slope, and I'm going to go x minus 3. Boom. So that is the equation of the normal line right there. Normal line. Excellent. Does that make sense for this if I had to graph it by hand? Sure, I hope it does. So I'm at this point. The slope is down 1 over 4, or up 1, back 4, up 1, 1, 2, 3, 4. So I was really far off, man. I'm a little disappointed by that. That is a bummer there. Let's try that again, and let's use official lines here and see if this looks any more normal than mine. That was rough there. So let's see. Is that making a right angle there? If I clean this up, I think that's more like this. That is looking pretty nice right now. So now with straight lines that I didn't freehand, that makes a right angle right here. So the tangent line is, here's the normal line all the way down here, is perpendicular to that. So we're going to graph these by hand on graph paper, and they should match up. Fantastic. Here are the rules. So this is the formal thing. So I was just kind of do it. Remember, if you take a derivative of constant as 0, so the derivative of 3 is just 0. Power rule we got. The constant multiple rule, that just allows us to do it essentially something like 2x squared when you did the 2 times the 2. The constant is this 2 in front. Those are all great, and the sum of difference allowed us to do multiple things like this. You may see this written differently. This u and v are actually functions, so you may see the derivative with respect to x of the f of x plus or minus, doesn't matter if you add or subtract, the g of x. So that's really what it means. It would be what? It would be, let's try that again. Oh no, I lost all that. Let's try that again. So what would happen? This just means the derivative of the u, so f prime of x plus or minus the derivative of g. So I'm going to use u and v because it's a shortcut for next. It's a shortcut for the shortcut for next section, but it really means this whole f of x, g of x if you prefer. Great job. That's the shortcut. Go practice these. The more you do, the better. It'll just start flowing. Good luck on the match check. Peace out.